So, good afternoon. Yeah, we've heard quite a bit of different use cases of drones and surveillance or monitoring, aerial photography. And I think that not many people are aware that there is another class of drones which has a little bit of a different use case in trying to provide green energy. I know this may sound a bit weird, so I hope that in the next 15 minutes I will give you a short overview of what's happening around that type of technology and where our company fits into that. So basically, why are we doing this? What's the problem? Well, obviously, if you look at this picture, you don't need many more words to describe what the problem is. So if this is the problem, how can we or how can technology try to fix that or to help alleviate the severity of these problems? Well, before we look at real specific technology solutions, we maybe first have to look at what is available. So to highlight the problem, where do we get renewable energy from in a sufficient quantity to actually, at some point or level, try to get rid of all the polluting energy sources that are available and try to get to a fully renewable energy planet or society. So this is a very nice graph. It was constructed by Stanford in 2006, and obviously you needed to went to Stanford to understand it. So it's a very nice. I thought for this audience maybe it will stick, but never. So I'm going to move over here so I can swipe my pointer around. Basically, the story behind this, and I won't go into any details. First thing is exergy. Yeah, that's not a spelling mistake. It's actually exergy. So for those of you who are a little bit knowledgeable about thermodynamics, it's closely related to entropy. Basically, it's the amount of energy that you can spend into a system where ultimately the system becomes into thermal equilibrium with its environment. Yeah? So this is just for the physicists we have in the audience. So what's the story here? There's only a few sources, main sources of renewable energy that we can tap into. Solar radiation, obviously, thermal crustal energy, driven by nuclear processes, and then there's gravitational energy. Those are actually the only three sources. So if we now look at the numbers, current use of energy over the world is roughly in the order of 15 terawatt per year. So 15 terawatts. So where do we get that power from? If we would tap all the geothermal energy, then you would get close to 32. So that's, we can grow on that. If you would tap all the ocean tides, then basically you get rid of all the tides, but you wouldn't be able to feed the world of its energy needs. So basically the only big renewable energy source that we have is solar radiation. Well, solar radiation obviously has solar panels. Solar panels very, very obvious, but actually wind energy and hydrothermal energy, or hydro energy, is actually some form of solar energy converted into a new source. So what we are looking at is actually this blue line where the current consumption plus many times over we could actually use to create a renewable energy source. Well, obviously, if you look at wind turbines today, we are doing exactly that, but there's a limited amount of technology available. These are, to some extent, renewable energy sources. Biomass is a bit frowned upon, and all the other sources are limited to only a few sources of technology that is available to tap into that natural resource. So what does that mean? So if I focus on wind energy, what we see is, and I'm sorry for the line stroke, it's a bit light, but okay. So if we look at wind energy available as a function of altitude, and we look at a reference altitude of 100 meters, which is basically the average hub height of a conventional wind turbine, then what we see is that for significant wind speeds that actually allow you to produce significant quantities of energy, then there's only a limited amount of space available in the world. And actually those locations are pretty much, either too far away from society to have a real impact, or they're already populated by conventional wind turbines. So if you want to expand this, where do you need to go? Well, this is the same picture, but now this is the available wind speed at an altitude of 250 meters. So the big difference between these two images obviously is the amount of available space on the Earth where you can actually deploy these kind of technologies in order to get the green energy that you want to achieve. So basically, by moving higher up in the atmosphere, we tap into a much larger resource of renewable energies than we are doing only today. So what's then the big issue? Well, there's a technology drive towards that. So making things bigger and higher ultimately means that you need to make bigger and bigger machines, which carry more and more material. And if you extrapolate basically the sizing, the scaling of conventional wind turbines over the last decade or so, you can see that yes, they're trying to push it up. They're trying to make them higher and bigger, and tap into these higher regions. But if you extrapolate this line, we would reach 250 meters somewhere around here. It's actually questionable if this line can be extrapolated. The amount of forces acting on these kind of structures become enormous if you build them higher and higher. So there's a technology bridge that we need to, technology gap that we need to bridge. So what would be one of the means of doing that? Simplest way would be you take a helium-filled shroud or balloon or whatever, and you stick a wind turbine generator onto that, and then you fly it up to 250 meters altitude. There's actually one company called Alteros, which is producing such a system, and they're in a pre-commercial stage where they're actually deploying these on off-grid sites. So if there's no infrastructure available for you to get your electrical power from, then these guys can actually supplement that by stationing one of their power stations. You fly a helium-filled balloon. It has a small 10 kilowatt sized generator. You can replenish your batteries, etc., etc. Another way of doing this is actually to make use of a phenomenon which is it's very well known. For instance, if you take a water skier behind the boat, if the water skier is driving at the same speed of the boat, then it can't overtake the boat, obviously, and it can't lag behind. It's always traveling at the same speed. However, if the water skier breaks out of the line of movement of the boat by going in a cross motion, then actually the speed of the water skier is increasing to above the speed of the boat itself, which is very good if you want to make flashy jumps and stuff like that. So you can use that same phenomena, which we call crosswind. So flying across the wind causes the system to accelerate and ultimately to fly at a higher speed than the wind speed itself, which is good in terms of energy yield, because then you can actually extract more power from that same airflow. So there's one company which is actually owned by Google X. They purchased these guys a few years ago, that is developing a similar system that we are doing, slightly different. There's a few choices that you can make. In this case, these guys are making an aircraft, a drone, fly with smaller wind turbines on top of the wing. So they generate power by flying these turbines through the air, and then ultimately, of course, you need to get that electrical power through the tether down to the ground. Another way of doing this is what we are doing, what Ampyx is doing. Basically, it's slightly more difficult to explain, but what we are doing is we are flying this repetitive motion, like a figure of 8 pattern. It doesn't really matter how you fly or what you fly, actually. But the effect of this is an increased velocity of the aircraft. The result of this is additional lift. The result of that is high tension in a cable, in the tether, that is mooring it to the ground. And now, by wrapping this tether on a spool, on a drum, you can actually create a rotational motion by exerting a force on this tether. Well, there's of course one downside. At some point, all the tether is up in the air, and you need to reset the system back to zero. If you would fly the exact same pattern, then obviously you would spend more energy in retracting it than you just produced. However, because we are a rigid wing drone aircraft, we can dive down in a diving motion and effectively reducing the tether tension to zero. So what we do is we produce power by creating this high-speed crosswind pattern, by expelling a tether from a drum. At some point, it's at maximum length. The aircraft dives down. You spool the whole thing back up again, and you only pay about 2 to 3% of the power you just created to reset the system back to zero. So now we have a power conversion mechanism. So why does this work? Yeah? Because what's the difference with respect to conventional wind turbines? Well, a conventional wind turbine is basically, if you look at this machine from a physics point of view, then where does the power come from out of this wind turbine machine? due to the scaling of power with velocity and force, you can actually literally say that the outer 30% of a wind turbine blade produces roughly about 70% of the total power coming out of the machine. If you now put on your economic glasses and you say, where are the costs located in this machine? Well, you know, the foundation, the mast, and the majority of these big turbine blades, they are costing a lot of money, but they are not actually contributing to the power equation. So that's weird. So from an engineering point of view, this is a silly machine. Everything that costs money doesn't do what you want, and the stuff that actually produces what you want it to do doesn't cost that much. So what would happen if you cut away all the bits and pieces that you don't need? Well, then you get our system, basically. And what we're doing is we are trading off getting close to the maximum theoretical limit of power extracting from the air, and we trade that off by sweeping a larger area. It's a different game, but ultimately the outcome is the same. So why do we do that? Why do we think this is important? Obviously, we don't need big installations. We don't need big masts. We don't need big foundations. We use about only 8% of the materials used in the conventional wind turbine, all else being equal. So for the same power, we actually reduce the total amount of materials used by 92%. And obviously, this has a huge impact on the actual cost of energy produced. So apart from the cost, which is like an economic driver, which is why we can run a company on this, there are some secondary benefits that are not totally obvious, but obviously visual impact. And I will show you a short video later on to show what kind of impact are we talking about in our system. Wake effect. So what I mean here is, paradoxically, our system can be put closer together in a park than conventional wind turbines because we don't have negative effects of the first line of turbines. And then, as I mentioned, the higher up you go, the more constant and the more wind is available. So all these factors together make this into a viable product. This is an old video, and I have to excuse me, but this is the only thing I could find on a quick notice. So this is the kind of visual impact. This is a 6-meter wing, which produces roughly about 20 kilowatts of power in this test. And you can see that this is a 600-meter tether. It's flying at 300 meters altitude. And you can see that the visual impact is significantly less. So this is one of the secondary benefits that we are looking for. So where is this technology today? Yeah? So where are the other companies in terms of the development process? As I mentioned, Alteros is very close to market. They have a commercial prototype that they're now certifying in order to be able to use and deploy this into airspace. Then we have our main competitor in similar technology, Makani. They have recently produced a video, and I will show that later on, of a 600 kilowatt, 28-meter span, completely autonomous drone that can actually hover as a normal quad rotor would do as well. And I'll show you that later on. So that's this video, and I will kill it slightly into it. But so here you see one of their prototypes, the earlier ones. This is not the 600 kilowatts version, but it gives you an idea of what kind of technology and how the system actually works in their case. So they are deploying their tether, they're flying up to their operational altitude. As soon as they hit that altitude point, they move into a crosswind pattern, which is happening roughly right now. And they start flying circles, generating lots of force, lots of speed. Their generators speed up, and they're actually producing power, converting it down to the ground. These are videos that are getting really boring really soon because the thing is just a repetitive pattern. There's nothing happening there. Yeah, okay. This is one of their recent videos of a launch test of their 600 kilowatt vehicle. As you can see, this takes a little bit more of effort in order to provide such a test. But here you see a octo-rotor, roughly 2,000 kilo aircraft, 28-meter span, hovering for deployment. And also, this is a fully autonomous test. So where are we? We actually have constructed a number of prototypes that we have been using to develop our control systems. As you can imagine, the aerodynamics, but also the flight dynamics of this system are highly nonlinear and slightly different from a conventional aircraft. So using conventional autopilot technology was actually no option for us, and we had to redesign the whole control system from scratch. and include our models where the aircraft is tethered to the ground. We are now in the design process of further scaling. So these guys produce about 20 kilowatts of power. The one that we are constructing right now, or designing right now, should be operational early next year. This one is producing roughly 250, 300 kilowatts. And our first commercial product will be a 28-meter, 30-meter wing, weighing 2.5, 3 tons. And that should produce roughly in the order of 2.5 megawatts of power. This is the flight video I wanted you to start. So how does our system look like from the tail camera? You actually missed the launch, but we are now using the tether force and the wind to get us to operational altitude, which is now. Now we're flying to a crosswind pattern. The tether, which you can see here, the tether is now being extracted from this drum, so we are generating power right now. In roughly the next turn, we would have to reset the system back to 0. You will see a diving motion with certain flap settings to decrease the airspeed, but that's not a big issue. So right around now, we would dive down back to the ground again. Yeah, so we are deploying crow setting to increase air drag a little bit. And after about 10 seconds, a bit less, we're at the minimum tether length again. So the flaps are closed and we're diving back into a crosswind motion very soon. So, and this goes on and on and on. All of these videos are completely autonomous. We have, obviously for safety reasons, we have human pilots in the background. To be honest, if the human pilot takes over, that generally leads to a crash. It's, the control system is so far better, so much better than the human pilot, that we have already 3 years ago, we've said, well, all the safety handling should be done by the aircraft and the control system, because any human intervention will lead to damage. Yeah, okay, I think maybe I'll just wrap it up and then I'll leave the other one if there's time. So, is this an opportunity, or are we, chasing a pie in the sky? Obviously, Disney, in their Big Hero 6 animation, they think at least that Alteros is barking up the right tree. And so they have here San Francisco powered by many different floating wind turbines. Maybe in the next animation they will use one of our systems as an illustration, who knows? So, I'll leave it up to you. Just to be fair with you, this is a very cash-intensive technology development. Right now, there's roughly 60 or 70 companies worldwide trying to do some form of this technology development. We are thinking that this is real and we can actually pull this off. So I'll leave it up to you to decide if we are crazy or not. But expect to see some of these systems in the next years to come. And actually, obviously, why are we here? Maybe that's a nice close-off. Yes, we are also looking for test sites, and we do see possibilities in Ireland. Thank you very much.